Hi, I am SHARAVAIAH, lecturer in mathematics from MBS Government Degree College, MAHABOOBNAGAR. Today we are discussed applications on fundamental theorem of integral calculus. In your Riemann integration, applications on fundamental theorem of integral calculus 1 or fundamental theorem of integral calculus. First we are discussed some definition. A statement of a fundamental theorem of integral calculus. Already we know that we have to prove that fundamental theorem of integral calculus 1 or fundamental theorem of integral calculus last class. Some definition. By definition 1, primitive, that is what is the primitive of the function f of x. Primitive of the function small f of x. Primitive. Let small f and capital F are two functions. Small f and capital F are two functions defined on closed interval a comma b if capital F dash of x equal to small f of x for all x belongs to closed interval a comma b, then capital F is called primitive of small f of x on closed interval a comma b. Definition: what is the primitive of a function small f of x? Primitive mean let small f and capital F are two functions defined on closed interval a comma b if capital F dash of x equal to small f of x, or sometimes f and g, where now we write f and g dash of x equal to f of x. F dash of x equal to, where capital F dash of x equal to small f of x for all x belongs to closed interval a comma b, then where capital F is called primitive of small f of x on closed interval a comma b. Suppose we define small f and g, let f and g are two functions defined on closed interval a comma b if g dash of x equal to f of x for all x belongs to closed interval a comma b, then g is called primitive of f of x on closed interval a comma b. Note, if f of x is a primitive of f of x on closed interval a comma b, where if capital F of x is a primitive of small f of x on closed interval a comma b, then capital F dash of x equal to small f of x and capital F of x equal to integration f of x dx. F dash of x equal to f of x, that implies capital F of x equal to integration f of x dx. Or if g of x is a primitive of f of x on closed interval a comma b, then g dash of x equal to f of x and g of x equal to integration f of x dx. Example: f from small f is a from small f from closed interval a comma b to are defined as small f of x equal to sin x, then find its primitive. Its primitive mean capital F of x or g. Okay. Since already we know that f dash of, where capital F dash of x equal to small f of x implies capital F of x is a primitive of small f of x. That implies f dash of x equal to small f of x, that implies where capital F is called primitive of f of x, that implies where capital F of x equal to integration small f of x. Integration small f of x dx, that implies where capital F of x equal to integration where small f of x mean sin x dx. Integration of sin x minus cos x, therefore minus cos x is the primitive of sin x. Minus cos x is the primitive of sin x. Already we know that fundamental theorem of integral calculus or fundamental theorem of integral calculus 1. There are two statements, both are equal. First one, if g is continuous function on closed interval a comma b and it is differentiable or derivable on open interval a comma b, and if g dash is Riemann integrable on closed interval a comma b, then integration a to b g dash of x dx equal to g of b minus g of a. First statement, if g is a continuous function on closed interval a comma b, that is differentiable on open interval a comma b, and g dash is Riemann integrable on closed interval a comma b, then integration a to b g dash of x dx equal to g of b minus g of a. Or another one, if small f is a Riemann integrable on closed interval a comma b and capital F is a primitive of small f of x on closed interval a comma b, then integration a to b small f of x dx equal to capital F of b minus capital F of a. Or integration a to b f dash of integration a to b capital F dash of x into dx equal to f of b minus f of a. Both are equal. Suppose where we consider capital F equal to small g, that is if f is a Riemann integrable on closed interval a comma b, g is a primitive of f of x on closed interval a comma b, then integration a to b f of x dx equal to where f of x mean g dash of, where because g is a primitive of f of x, g is a primitive of f of x mean g dash of x equal to f of x, that is then integration a to b f of x dx equal to f of b minus f of a, or integration a to b f dash of x into g f dash of x dx equal to f of b minus f of a. Both are equal. That implies, okay, that is, these are the statement of the fundamental theorem of integral calculus. Okay, problems. First one, if g of x equal to x to the power of n plus 1 by n plus 1 such that for all x belongs to closed interval a comma b, then find integration a to b g dash of x dx. Already sometimes the question in terms of using by the fundamental theorem of integral calculus, find out the integration a to b g dash of x dx, where g of x equal to x to the power of n plus 1 by n plus 1. Okay, if g of x equal to x to the power of n plus 1 by n plus 1 for all x belongs to closed interval a comma b, then find integration a to b g dash of x dx using by the fundamental theorem of integral calculus. Okay, easily we have to find out using by the fundamental theorem of integral calculus, where given that g of x equal to x to the power of n plus 1 by n plus 1 such that for all x belongs to closed interval a comma b, where 1 by n plus 1 is a constant. That implies g dash of x equal to 1 by n plus 1 is constant too, where the differentiation of x to the power of n mean n into x to the power of n minus 1. That implies where differentiation of x to the power of n plus 1 mean n plus 1 into x to the power of n plus 1 minus 1 plus 1 minus 1 get cancel, n plus 1 cancel. That implies g dash of x equal to x to the power of n. Okay, therefore g dash of x equal to x to the power of n, that implies automatically g dash of x is continuous function for all x belongs to R. G dash of x is a continuous function for all x belongs to R. That implies g dash of x is continuous function for all x belongs to closed interval a comma b. Already we know that by previous theorem, every continuous function on closed interval a comma b is must be Riemann integrable. Every continuous function on closed interval a comma b is must be Riemann integrable. Therefore, where g dash is continuous function on closed interval a comma b, that implies g dash is Riemann integrable on closed interval a comma b. Therefore, where we observe that g of x is also continuous function on closed interval a comma b, because where x to the power of n plus 1 by n plus 1, therefore for any interval where g of x is a finite value, that implies g is continuous and g is derivable and g dash is Riemann integrable on closed interval a comma b, where g is continuous function, g is derivable on closed interval a comma b, and g dash is Riemann integrable on closed interval a comma b. That is where g satisfies all conditions of a fundamental theorem of integral calculus. Therefore, by fundamental theorem of integral calculus, g is continuous function on closed interval a comma b, g is derivable on open interval a comma b, and g dash is Riemann integrable on closed interval a comma b. Then fundamental theorem of integral calculus 1, we get integration a to b g dash of x dx equal to g of b minus g of a. Integration a to b g dash of x dx equal to g of b minus g of a. That implies where integration a to b mean integration 0 to 1 g dash of x dx equal to integration, okay, integration a to b g dash of x dx equal to integration a to b, where g dash of x equal to x to the power of n, that implies x to the power of n dx, that equal to g of b minus g of a, where g of x equal to x to the power of n plus 1 by n plus 1. That implies g of b equal to substitute x equal to b to the power of n plus 1 by n plus 1, where g of a equals substitute x equal to a to the power of n plus 1 by n plus 1. That implies g of b minus g of a. Therefore, where g of b equal to where g of b equal to b to the power of n plus 1 by n plus 1 minus g of a equal to a to the power of n plus 1 by n plus 1. 1 by n plus 1 taken LCM is common. 1 by n plus 1 into b to the power of n plus 1 minus a to the power of n plus 1. Therefore, using by the fundamental theorem of integral calculus 1, if g of x equal to x to the power of n plus 1 by n plus 1 for all x belongs to quotient A, comma b, then find. Then integration a to b g dash of x dx equal to 1 by n plus 1 into b to the power of n plus 1 minus a to the power of n plus 1. Okay. Next, second one. If the function phi of x is equal to minus 1 by 2 into x square such that x less than 0 and phi of x equal to 1 by 2 x square such that x greater than or equal to 0, then find integration minus a2 plus a minus a to a phi dash of x into dx, where the function phi of x is defined as phi of x equal to minus 1 by 2 x square such that x less than 0 and phi of x equal to 1 by 2 x square such that x greater than or equal to 0, then find integration minus a to a phi dash of x into dx. That is, we are given that the function phi of x is defined as phi of x equal to minus 1 by 2 x square such that x less than 0. Second one, 1 by 2 x square such that x greater than or equal to 0. Phi of x equal to minus 1 by 2 x square such that x less than 0, 1 by 2 x square such that x greater than or equal to 0. Where now we have to find out phi dash of x using by the phi of x. That implies phi dash of x equal to, where we have to find out the phi dash of x. That implies phi dash of x equal to minus 1 by 2 into x square differentiating to x such that x less than 0. Second one, 1 by 2 into x square differentiating to x such that x greater than or equal to 0. That implies where phi dash of x equal to minus 1 by 2 into 2x such that x less than 0, 1 by 2 into 2x such that x greater than or equal to 0. 2 get cancelled, 2 get cancelled in both equations. That implies phi dash of x equal to minus x such that x less than 0, x such that x greater than or equal to 0. Where we have to find out the integrand value minus a2 plus a. That implies, that is phi dash of x equal to minus x such that x less than 0 or x belongs to closed interval minus a comma open interval 0. And second one, phi dash of x equal to x such that x greater than or equal to 0 or x belongs to closed interval 0 comma a. Therefore, where the function phi dash of x, it is defined as phi dash of x equal to minus x such that x less than 0 or x belongs to closed interval minus a comma 0, x such that x greater than or equal to 0, x belongs to 1. Therefore, phi is satisfied all conditions of a fundamental theorem of integration, where clearly phi dash is Riemann integrable, phi is continuous and phi is derivable. Therefore, phi is continuous on closed interval minus a comma a, phi is derivable on open interval minus a comma a, and phi dash is Riemann integrable. Therefore, phi is satisfied all conditions of a fundamental theorem of integral calculus 1. Therefore, by fundamental theorem of integral calculus, we get integration a to b g dash of x dx equal to g of b minus g of a, where g mean phi. Therefore, integration a to b phi dash of x dx equal to phi of b minus phi of a. Integration a to b g dash of x dx equal to phi of b minus phi of a. Therefore, integration minus a to a phi of x into dx equal to phi of a minus phi of a. Therefore, phi of a where x greater than 0, that implies phi of b mean a square by 2 minus of phi of minus a square by 2. Therefore, a square by 2 plus a square by 2 2a square by 2, that equal to a square. Therefore, the function phi defined as phi of x equal to minus 1 by 2 x square such that x less than 0, phi of x equal to 1 by 2 x such that x greater than or equal to 0. That implies integration minus a to a phi dash of x dx equal to phi of b minus phi of a, that equal to a square. Okay, next one, if phi of x equal to e to the power of x for all x belongs to closed interval a comma b, then find integration a to b phi dash of x into dx using by the fundamental theorem of integral calculus. Okay, therefore we are given that phi of x equal to e to the power of x for all x belongs to closed interval a comma b, where phi of x equal to e to the power of x, that implies phi dash of x equal to e to the power of x. That implies already we know that exponential function it is continuous for all x belongs to R. Phi dash is continuous function for all x belongs to R. That implies phi dash mean e to the power of x. E to the power of x is continuous function for all x belongs to closed interval a comma b. Already we know that by previous theorem every continuous function on closed interval a comma b is must be Riemann integrable. That implies where phi dash is a continuous function on closed interval a comma b, that implies phi dash is Riemann integrable on closed interval a comma b. Therefore where phi is continuous, differentiable and phi dash is Riemann integrable, that is phi is satisfied all conditions of a fundamental theorem of integral calculus 1, then integration a to b g dash of x dx equal to g of b minus g of a, where g mean phi, that implies integration a to b phi dash of x into dx equal to phi of b minus phi of a, where phi of x equal to the power of x, that implies phi of b equal to e to the power of b, phi of a equal to e to the power of a, that implies integration a to b phi dash of x dx equal to e to the power of b minus e to the power of a. Next, fourth one, using by the fundamental theorem of integral calculus, show that integration a to b 1 by x square plus 1 dx equal to tan inverse of b minus tan inverse of a. Using by the fundamental theorem of integral calculus, show that integration a to b 1 by x square plus 1 dx equal to tan inverse of b minus tan inverse of a. Given that the given integrand can be comparing to integration a to b g dash of x into dx, that is the given integration value it is comparing to integration a to b g dash of x into dx, because we are using by the fundamental theorem of integral calculus, where we have to find out the integration value using by the fundamental theorem of integral calculus. Therefore the given integration it is considered to equal to integration a to b g dash of x dx. Integration a to b g dash of x dx equal to integration a to b 1 by x square plus 1 dx. That implies where g dash of x equal to 1 by x square plus 1 for all x belongs to closed interval a comma b. Therefore for any interval automatically we observe that g dash of x is defined for all x belongs to closed interval a comma b. That implies g dash of x is continuous function on closed interval a comma b. G dash of x is continuous function on closed interval a comma b. That implies since every continuous function is Riemann integrable, that implies g dash of x is Riemann integrable on closed interval a comma b. And where g of x equal to, already we know that the primitive mean, where phi dash of x equal to phi of x, that implies phi of x equal to phi of x equal to, where that implies g dash of x equal to integration g of x into dx. Therefore where g of x equal to integration 1 by x square plus 1 to dx. Integration of 1 by x square plus 1 mean tan inverse x. That implies where g of x equal to tan inverse of x. Therefore g is satisfied all conditions of a fundamental theorem of integral. G is continuous and next one derivable, next one g dash is Riemann integrable on closed interval a comma b. That implies g of x is satisfied all conditions of a fundamental theorem of integral calculus. Therefore by fundamental theorem of integral calculus we have integration a to b g dash of x dx equal to g of b minus g of a. Integration a to b g dash of x dx equal to g of b minus g of a. That implies integration a to b where g dash of x mean 1 by x square plus 1 dx equal to g of b minus g of a, where g of x equal tan inverse of x. So that implies where g of b equal tan inverse of b, g of a equal tan inverse of a. Therefore integration a to b 1 by x square plus 1 dx equal tan inverse of b minus tan inverse of a. Therefore using by the fundamental theorem of integral calculus 1 we have to show that integration a to b 1 by x square plus 1 dx equal tan inverse of b minus tan inverse of a. Similarly next one, using by the fundamental theorem of integral calculus to show that integration a to b x dx equal to 1 by 2 into b square minus a square. Okay, that is the given integrand value it is comparing to integration a to b g dash of x dx. Given that integration a to b g dash of x dx equal to integration a to b x dx, that implies where g dash of x equal to x. That implies x is a continuous function for all x belongs to R. X is a continuous function for all x belongs to R. That implies g dash is continuous function for all x belongs to R. That implies g dash is continuous function on for all x belongs to closed interval a comma b. Already we know that every continuous function is Riemann integrable. That implies g dash is Riemann integrable on closed interval a comma b. Therefore Therefore, where g of x equal to integration g dash of x into dx, where g dash of x equal to x. Therefore, g of x equal integration x to dx, that equal to x square by 2. Therefore, where g satisfied all conditions of a fundamental theorem of integral calculus 1, then integration a to b g dash of x dx equal to g of b minus g of a. Therefore, integration a to b x dx equal to, where g of b mean b square by 2, g of a mean a square by 2, that equal to 1 by 2 into b square minus a square. Therefore, it is the using by the fundamental theorem of integral calculus we have to find out the integrand value. Thank you.